Well, let's see if we can find something else here that was in the book. That was this one. Now on this one is the one we need to talk about, the transfer. This is when it gets fun. Or this basically is the non-centroidal axis, and how are we going to calculate that? And this is the one, if we look, and note on these centroidal axis deals here, what's going to happen is, if you looked in the book there on page 159, they break this thing up into many different areas. And then they're calculating each one of the centroids, and they're making that relative to this centroidal axis. So there's each one of these would have a different number relative to that axis, wouldn't it? And you have to do a summation of the centroid of each, or excuse me, the moment of inertia of each one plus the area times that particular distance. So there's going to be a formula we're going to be seeing here in just a couple minutes where it's the moment of inertia of each one of these pieces plus the area of each of those pieces times some distance d squared, and that's the distance from the centroidal axis to each one of these individual centroids. And you'd have to sum all those up, and that would give you the moment of inertia. But all right, now with these particular ones, all we have to worry about are these formulas right here. The moment of inertia for the x, the moment of inertia for the y. And then, of course, the moment of inertia about the reference point at the bottom, if you will. Okay? So don't get too hung up on that. But what we are going to do, so basically, that's where it's more of the calculus type thing where you start doing, you add all those up, you know, in infinitesimally small amounts, you know, and this is what they came up with. Okay? So that's how they derived at that. Now, it talks about the transfer formula on page 160, and that's this, what's going on there? That, I guess, where you have to use this distance d. Okay? So, the transfer method talks about, and they show this equation, I think it's equation 8.3. The moment of inertia is equal to the moment of inertia of the individual piece plus an area of that and a d squared. The d has to be squared because, remember, this moment of inertia is inches to the fourth, right? This area is inches squared, and this would be in inches, the distance, okay? So it has to be squared. So it can also be inches, you know, this has to be inches to the fourth as well. Excuse me, or you can't add it up. So what's going to happen there? So note, this is the moment of inertia with an area with respect to any axis. So we can make this xx anywhere we want to and say, tell me the moment of inertia relative to this axis as opposed to relative to this axis. Because essentially relative to the centroidal axis, we just go up here, whoops, and use these formulas for this square, right, or this rectangle, okay, because that's a centroidal. But if we want to find it about the bottom here, or anywhere along that, not necessarily the bottom, but anywhere in space, then we use this formula. And then we're going to take that one step farther, and if we've got a composite shape, we'll take all of that stuff and add them together. Or in the case of the hollow, subtract it out. So that's where we're headed. And where would that be of use? On like an I-beam? Yeah. An I-beam, or you can even do composite type pieces where you might have a, they show an example of a plate on top and a plate on the bottom of an I-beam. So you have to figure out what the moment of inertia of that is, you know, if they're welded together. So, but, so then that's the moment of inertia. Yeah. With respect to any axis, this is the moment of inertia of the individual piece here. Whether it's that square, rectangle, whatever shape you've got. This is the area of that piece. And then this D is going to be the distance from the centroidal axis of your original piece to where you're trying to find it relative to that new axis. Okay? So this will make a little bit more sense here when we get to a good picture. In fact, it's going to be this picture right here. This will probably bring it together. I sure hope. This one right here. Let's see if we can make that a little smaller. Okay, so we can find this relative to, and that's really not the picture. That's not the picture I want. But this is just showing you a composite area, but I'm going to go one picture better than that and show you what and this XX, that would be the centroidal axis, right? Okay. That, but I don't want that picture really. I want a different one. This one. See if we can make that smaller. This picture, figure 8.8, that's actually on the top of page 162 if you're following in the book. Okay, so that shows the location of the centroidal axis, and then the reference axis, and the Y centroidal axis as well, right? But what we might, if we, when we calculate what the moment of inertia of this whole composite shape is, what we're going to be doing is we're going to be going in there and we're going to find the moment of inertia of this particular shape, the top. Then we're going to find the moment of inertia of this particular shape, which is the center. And then, of course, the moment of inertia of that shape. Well, when we do that, we're going to find the center of gravity of each of these individual pieces, right? And then we're going to find that with this inverted T-shape almost, we're going to find the center of gravity of the whole thing, right? So the center of gravity of this whole thing, I don't know, it looks, well, it shows you here basically, I think. It's going to be a little bit above this center of gravity of this piece, right? So we're going to have the center of gravity of this one relative to this. That's going to be a distance. We're going to have a distance from here to here, and then a distance from here to here. So to find the moment of inertia of this whole big thing here, and this is really spelled out, I think, kind of good on the handouts I gave you. I guess was that last week? On the last page. The last page. That's why I didn't really want to. I don't really want to get rid of that handout, because that moment of inertia of composites is probably going to be the one that's going to be the the handiest for you. But what that says then is the moment of inertia is going to be the summation of the moment of inertia of each of the individual pieces plus the area times the distance squared, where this D is going to be the difference, if you will, between the center of gravity of each piece and the center of gravity of the composite. That one little spot right there seems to be where most people get hung up. Is what does this, how do I find this D value? Okay, so if we had, on this particular problem, if we go in there and do that, what we're going to do is we're going to have, we'll have to go in and find the Y bar. So to do that, we would do what? The area of 1, well, and let's, now they're showing this as 1 is on the bottom, 2 is in the middle, and 3 is in the top. So the area of 1, and that's going to be what? 6 times 1. So 6 square inches. The area of 2 is going to be what? 1 by 12. Thank you. So 12 square inches. And area 3 is 1. Actually, it's 12 by 1. 12 times 1, isn't it? Base times the height. 12 square inches. Then we have to have the Y bar, or the Y for 1, Y for 2, Y for 3. Okay, so what is the Y for 1? 1 divided by 2, right? See, you thought you weren't going to have to remember this ever again? So it's a 1/2 inch. That's the distance from the base up to this center of gravity, right? Then we have to get the Y for 2, which is going to be 1 plus what? This is 12 inches, so it's 12 divided by 2, which is 6, right? So 7 inches, which would be half of 14 anyway, wouldn't it? Because each of these are 1 inch, so it's somewhat symmetrical on the Y. And then finally the third one is going to be what? 13 plus 1 divided by 2, so 13.5 inches. Now then, to find our moment of inertia about this whole composite, we're going to have D1, D2, and D3. D1, okay, so what we found out was, and you could call this, if we called this Y1, we could actually call that CG1. This would be CG2 and CG3, wouldn't it? Because that's the center of gravity. This would be CG3. This one was CG2, and this is CG1. Okay. Well, we can't figure out what D1, D2, and D3 are yet, because we have to have the center of gravity for the total first. Because those D values are the difference between the center of gravity of each piece compared to the center of gravity of the composite, the whole thing. So we have to figure out what Y bar is. So let's go and figure out what Y bar is. Y bar was what? The area of the first one, which was 6, right? Bless you. Times Y1, which was 1/2. Again, bless you. 12 square inches times 7, right? plus 12 square inches times 13.5. All of that divided by 6 plus 12 plus 12. So somebody punch that in for me.
9.2.
How much?
9.2.
9.2. So we were right, weren't we, in our assumption that this center of gravity of the total, and that's what that is, right? That's, if you will, CG total. That's based on the way that thing is shaped. To me, since it's top heavy, if you will, I can find my cursor. Since it's longer up here on top than it is on the bottom, to me that told me it was top heavy. So instinctively I knew that the center of gravity had to be above the center line of that 14 inches. And it does tell me that it is a difference then. So now what I want to do is I want to find the difference between the center of gravity of this total and the center of gravity of each of these pieces. So from the center of gravity of this first piece up to that center of gravity of the total is going to be what? 9.2
8.3
minus, huh?
I think
This?
Yeah. I get 8.2 or 8.3 when I type that in.
Okay, I need some confirmation here. I got two 9.2s. 6 times a half.
The book says 8.3 also.
6 times a half.
8.2 or 8.3.
8.3?
Yeah.
Using my numbers, right?
Yeah.
Okay. Okay, you other guys, then you better sharpen your calculator up then. Okay. Well, see, and that's why it's nice to follow along and figure out where you made those mistakes with your calculator. 8.3?
8.3, yeah.
Okay, you don't have to holler.
Sorry.
I'm just kidding. Okay, so we want to get rid of that, don't we? So then it's just a matter of taking the difference between those two numbers. So it's 8.3 minus a half inch, right? So what's that? Let's see. 7, 6, 6.8, no, 7 inches, right? Okay, then we got 8.3 minus 7, 1.3, and then 8.3 minus 13.5. Ooh, punch that in. Let's see, what's that going to be? How much? 5 point what? 2 inches. And really, you don't have to have the minus in there. It's just the difference between the two. It's an absolute value. Okay?
It's going to get squared anyways.
Right. So when you square it, it's going to be a positive value. So it really doesn't matter. Okay? Does that make sense? Those are the things we have to have. We don't have to, from this point forward, we don't have to have that Y1, Y2, and Y3. All we need to be concerned with now, and you can see it right here, we need the moment of inertia of each individual piece plus the area of each individual piece plus the D number now squared. So we can forget about the Y and the Y bar at this point for what we need to use to calculate. But if we want to,
you had to calculate it to get to D.
right?
Yeah.
You still
Yeah.
had to be able to do the Y's and the Y bar. So we can't forget chapter 7. Okay, but we can now. We can suspend it now. We can suppress it like we do in CAD, right? So yeah, we don't want to get rid of anything. Once we calculate it, we leave it on there. We might need it later on. Okay. So then to find the moment of inertia about this whole thing on the centroidal axis, right? we're going to take the moment of inertia of each individual piece. Oh, we didn't calculate that yet, did we? So we need to have the moment of inertia for each individual piece. So 1, 2, and 3. Well, what did we decide? That was the base times the height cubed, right? So the base of the first one is 6, and it's 1 cubed divided by 12. And by the way, you won't have to memorize any of those formulas, right? You'll have your sheets now on the test, so don't panic on that, but you're going to be able to use whatever. Moment of inertia of the second one, excuse me, is 1 times 12 cubed, right? That was 12, wasn't it? Yeah. Divided by 12. And then the third one is, was that 12? How wide was that? Was that 12? Yeah, 12. 12 is the base. 1 is the height cubed divided by 12. So what are those numbers? This one is 0.05?
Wouldn't that be 0.5?
Oh, 0.5, okay. Sorry, I might have misunderstood what you were saying. You gotta speak up. I don't have my hearing aids turned up very loud. 0.5 inches to the fourth. What about the second one? 183.1. 183.1. You're reading them out of the book. Are you cheating?
No.
Okay.
No, because out of the book it says 144.
Huh?
144 is in the book.
Oh, 144. Well, maybe we better check our calculator then, huh? Do what?
12 to the third divided by 12 is 12 squared, and that's 144.
You're right.
Then the third one is 1. Excuse me. So now we can solve for that. Can get it all on there. So the moment of inertia for the first one was a 1/2 inch. So 0.5. I'm not going to put the units in here. Plus the area of the first one, which was 6, times D, which was, see, was that 7.8? And that number has to be squared, plus the moment of inertia of the second one, plus the area of the second one is 12 times D2, which is 1.3 squared, plus the moment of inertia of the third one, which was 1, plus the area of the third one, which was 12, times D3, which was 5.2 squared.
Where did you get this equation?
Where'd I get what?
This equation?
That is, it's actually on page 163. Let's see, it probably is.
It's on this handout too.
Right. That's, well, I was trying to find it in the book for him. Well, you can look on page 163. It's up at the top. Equation 8.4. Summation of the moments of the individual components plus the area times the distance squared, and that distance is the difference between the center of gravity of each individual piece and the center of gravity of the overall piece. And you punch all that in, and hopefully you get something like what?
855.
Yeah. So what you got? Yes, sir?
So we only use IOX,
Well, if we were, this is the moment of inertia about the x-axis. If we were trying to do it about the y, then we would have to do it. It would have to use the y calculations. Yeah. Note though that in the example problem we're going to do, it does ask you to do it about the y-axis. And the nice thing about it, when you've got symmetrical parts like we were talking earlier, the distance that you've got to deal with, that d value there, 0. There's no difference between the if it's symmetrical, there's no difference between the distance this way on the individual components as opposed to the overall component. So if that distance is 0, then that negates that whole second part of that equation. So then all you're dealing with is the moment of inertia of each of those individual pieces. It actually becomes easier. Yeah, it's much easier at that point.
So it would just be the 0.5 plus 144 plus 1?
No. It would be the 6 plus 12 plus 12 divided by, or excuse me, oh yeah, I was looking at the wrong calculation. Yeah, the 0.5 plus 144 plus 1.
Don't we have it on IOY then, which is
Do what?
HB3 over 12?
Well, but it wouldn't be, I
it
stand
would be
corrected,
if
it
we
wouldn't be those numbers because you would have to go back and calculate it
Yeah.
because your moment of inertia would change for all of
So you
those.
would just use those numbers and add them up, though,
Right.
whatever those were.
Yeah.
Yeah.
You'd use the same type of numbers, but it would be different numbers because it's the height divided, or height times base cubed divided by 12 instead. So yeah, so it wouldn't be the same numbers. Wouldn't be that easy. Wouldn't it be nice? I guess if it was square, it would be, wouldn't it? Some kind of square thing going on. So, is this making sense? It's basically you're just plugging in a bunch of numbers. This is definitely the plug and chug part. Well, let's see. Was that the example? No, there it is. Okay, so where is it? There it is. Example 8.6. Let's look at that one real quick. So in example 8.6, let me get my picture out
Before we
here.
move on real quick, can you scroll up? So does the force have to be coming down on the center of that I-beam?
Let me get this and I'll come back to it. I just need to get that side. Is the what?
Does the force have to be coming down on the center of the I?
No, we're not. There's no force involved here.
Okay.
This is just what can this cross section handle.
You know what I'm saying? If there were a force and it was coming down on the I-beam,
Mhm.
would it have to be on the center for that moment of inertia, or could it be off to the right or left, or it doesn't matter? As long as it's coming down on
We're not dealing with the force on this.
Okay.
Period.
All right.
We're not. That's coming later.
Okay.
Okay. This is just what the resistance. This is just some. It's a kind of a mythical number that says this is what this can resist. It's a resistance value. Okay. And that's all you can say about this at this point. All right. Now, excuse me. Let's look at example 8.6, and we've got quite a bit more stuff to cover. I know there's no way we're going to do it today. So, but I at least want to get through this example problem, and it's similar to what you've just seen here.